Hello everyone, today we are presenting on the diffusion model translation or the DMT for image-to-image translation. We will explore a novel approach that addresses some of the challenges in this exciting field. Let's begin by understanding the core task the paper focuses on, image-to-image or eye-to-eye translation. This refers to the process of converting an input image from one domain to an output image in another domain while preserving key semantic content. It's a foundational task in computer vision with broad practical impact. As illustrated in the example on this slide, we might want to convert a sketch into photorealistic portrait, transform a segmentation mask into a natural scene, applying stylistic changes like turning a photo into van, or some other image-to-image translation task. But each of these applications require maintaining essential structure of the original while altering its appearance to fit new domain. The paper mainly focuses on improving the efficiency and effectiveness of this translation process, especially under the diffusion model paradigm. Now let's look at how this task is typically approached. Broadly, existing methods fall into two families, GAN-based and diffusion-based models. GAN-based methods like pix-to-pix, spade and scene use adversarial training where a generator learns to produce realistic outputs that can fool a discriminator. These methods are fast, powerful, but suffer from instability, mode collapse, and difficulty in capturing fine-grained details. Whereas diffusion models, including recent advancements like Palette and SD did, offer much more stable training and superior sample quality. These models work by gradually adding noise to an image and then learning to reverse this step-by-step process. However, a key limitation with diffusion-based eye-to-eye method is shown in the diagram given below. These models inject source information into every denoising step. This means they must condition on the source repeatedly, making the translation computationally heavy, slow to train, and harder to scale. The paper addresses this inefficiency by proposing a simpler alternative. As previously mentioned, existing models translate at every single diffusion step at timestamp t. They map a noisy source image xt to an intermediate representation yt using a learned function ftx. This means that the model learns a different translation for every level of noise. This creates three main problems. First is redundancy, since translation is done repeatedly. Second is high computational cost due to repeated conditioning. And third is increasing training complexity because learning translation over noisy input is more difficult. The diagram well illustrates this repeated conditioning process throughout the reverse diffusion, which the paper identifies as a major inefficiency. So they proposed a DMT solution called the diffusion model translator. The core idea is simple but powerful. Instead of translating at every step, the model performs translation only once at a fixed time step t. Here the noisy source image xt is mapped to its target counterpart yt using a single learned module. After this translation step, the rest of the reverse process from yt back to y0 is handled using a standard pre-trained DDPM without any further conditioning on the source. This design brings three key benefits. First, it reduces the number of translation operations to just one. Second, it works with a single noise level, simplifying training. And third, it makes the architecture modular by allowing the reuse of pre-trained diffusion models. As we can see in the diagram, this result is a much cleaner and more effective pipeline compared to prior method. Now let's dive into the theoretical justification why this simplification works. The answer lies in the symmetry of the forward diffusion process. Both the input x0 and the target y0 undergo the same Gaussian forward process, which gradually corrupts them into noise. As t increases, both xt and yt begin to resemble pure noise, specifically normal distribution. Because of this shared latent space at time step t, it becomes sufficient to translate xt to yt at single point in time. This paper takes advantage of this property to perform the translation just once, relying on the DDPM to handle the reconstruction of Y naught. However, there's a trade-off. At high time, the input is highly noisy, making translation easier but precise. At low time, there's more structure in the input, but translation becomes more difficult. The paper analyzes this trade-off and selects an optimal time step, which we are going to see. Now the question arises, how do we choose the right time step? Now let us imagine we start with a clean input image x0 and its target output image y0. Now we apply the same amount of Gaussian noise to both of them using a diffusion process. This gives us noisy version xt and yt. As we increase the noise level, that is, as time step t approaches the final t, both xt and yt start to resemble pure noise drawn from a standard normal distribution. In this state, their distribution, essentially xt yt, uh, essentially resembles with the normal distribution. This means the distance between xt and yt gets smaller, which is good for translation because it becomes easier to learn a function that maps one to another. But there's a problem. As t increases, the noisy input xt becomes less and less like the original image x0. So while translation becomes easier, the amount of information retained from the input drops, and that's bad for conditioning. So we are kind of facing a classic trade-off. High T translation is easy, but the input signal is weak. Low T input signal is strong, but translation becomes harder. And that's exactly what we are trying to solve. So now let's look into the trade-off curve. Uh, on this, we can here see a plot where the red curve shows the distance between xt and yt. This measures how hard or easy it is to translate between the two at a given noise level, whereas the blue curve shows the distance between the original image x0 and its noisy version xt. This captures how much information from the inputs survives the noise. Now as we increases t, notice what happens. The red curve goes down. This means the translation becomes easier, which makes sense because both images are being pushed toward the same noisy distribution. And for the blue curve, which goes up, that means we are losing more of the original information in XC, again expected as the image becomes more corrupted. The key insight is the intersection point where both curves are balanced. This is the sweep point, the noise level where xt is still close enough to x0 to retain meaningful input, but also close enough to yt to make translation learnable. We call this optimal time step t, and selecting it carefully is one of the secret behind DMT effectiveness. Now let's look into the mathematical aspect.
Greetings everyone, myself Manan. I will walk you through the methodology of our model. In our proposed approach, image to image translation is achieved using a three-step process involving a forward diffusion process, a domain translation step using a learnable module, and a reverse diffusion process. We now describe each of these steps in detail. Step 1. In the first step, we begin with a clean source image denoted as X node, which belongs to the source domain, example sketches, line drawings, or grayscale images. We then apply a forward diffusion process to this image. This process adds Gaussian noise in a gradual and controlled manner across a predefined number of time steps, typically denoted by T. The output of this process is a noisy image xt at an intermediate step t. This process is governed by a predefined schedule denoted by beta 1 to beta t, where beta t belongs to 0 to 1, controls the variance of the noise added at each step. The resultant distribution after t steps is shown by q xt given x naught. Here, alpha t bar denotes the multiplication of alpha I from I is equal to 1 to t, and I is the identity matrix ensuring isotropic noise. This formulation means that at a time step t, the image xt is a scaled version of the original image x0, corrupted with Gaussian noise. This noisy image maintains the essential structure of the original image while discarding the fine details. The forward diffusion process is not learned, it is deterministic and fixed for all samples. This step prepares the source image for translation in a common latent space where both the domains are represented under noise. The degree of noise can be controlled through T, allowing us to balance content preservation with domain adaptation in the next step. Step 2 is the domain translation using DMT. Once we obtain the noisy image xt, we perform the domain translation at the time step t. This is the core of our method and is executed using a learnable translator network called the Diffusion Model Translator. The idea here is that xt belongs to the source domain but has been noised in a way that suppresses low-level domain-specific features. We aim to map this presentation to a noisy image yt, which lies in the target domain but at the same noise level. This mapping only happens once at time step t, which makes our method efficient compared to the approaches that inject source information at every denoising step. This stage transforms domain semantics while preserving the general structure and content of the image encoded in xt. Next, we have step 3. The final step involves denoising yt, the noisy translated image in the target domain, to obtain the clean final output y0. This is achieved using a pre-trained diffusion model trained exclusively on target domain images. The denoising process uses a learned recursive diffusion model which starts at yt and proceeds backward from timestamp t to 0, removing the noises step by step. This denoising model, typically implemented as a unit, learns to predict either the original image or the added noise. It reconstructs y0 through a series of probabilistic updates until a clean, high quality image in the target domain is recovered. Importantly, this step requires no information from the source image or domain. Since YT already contains translated semantics, the denoiser only needs to refine the image by removing the noise. Together, these three steps, forward diffusion, translation at single timestamp, reverse denoising, form the complete DMT based image to image translation pipeline. In the following sections, we will look at the detailed mathematical formulations behind these steps. Now, let's explore the mathematics behind step 1 and step 3, the forward and reverse diffusion processes. Starting with step 1, forward diffusion. This step applies a series of Gaussian noise additions to a clean image x0, resulting in a gradually corrupted version xt. The formulation for this forward noising process is q xt given x0 is a normal distribution of xt, where the mean is under root alpha t bar x0 and the variance is 1 minus alpha t bar identity. Here is what each term means. Q xt given x0 is the conditional probability of the noisy image xt given the original clean image x0. Alpha t bar is a multiplication of the alpha I where I ranges from 1 to t. The term under root alpha t bars x0 ensures that the signal strength decreases gradually. The term 1 minus alpha t bar identity defines the growing noise variance as t increases. This formulation allows us to directly sample xt from x0 at any timestamp t rather than simulating each step individually. Now, step 3 is the reverse process. The reverse diffusion. The reverse diffusion is modeled as a learned denoising process. It aims to reconstruct the clean data y0 from a noisy image yt. The reverse distribution is modeled as p theta y of t minus 1 given y of t is a normal distribution of y of t minus 1 with the mean as mu theta yt comma t and the variance acts as sigma theta yt comma t. Here, mu theta is the predicted mean, often modeled by a neural network like a unit. Sigma theta is the predicted or fixed variance of the Gaussian. Theta represents the parameters of the learned denoiser. This process is repeated iteratively until the final denoised image y0 is obtained. A common training simplification is to directly train the network to predict the added noise epsilon instead of the mean. This leads to the simplified loss as epsilon minus epsilon theta xt comma t whole square. This formulation is the backbone of the modern diffusion models. and applies equally to our DMT approach, where denoising happens only in the target domain. Let's now discuss the core of our approach, step 2, domain translation using the diffusion model translator. The objective here is to inform a noisy source domain image xt into a noisy target domain image yt, all at a single timestamp t. Instead of relying on recurrent conditioning, we do this with a single function given by p of theta yt given xt is equal to dmt with the parameter theta and input xt. The function dmt theta is a neural network trained to learn the mapping from noisy source to noisy target image. To train this network, we use paired clean images x0 y0 from the source and target domains respectively. We apply the same forward diffusion process and use a shared noise epsilon that belongs to a normal with mean 0 and identity as the variance. To generate xt and yt, here xt is given by under root alpha t bar x0 plus 1 minus alpha t bar epsilon. Similarly, yt, because the same noise is applied to both, the difference between xt and yt captures only the semantic domain gap. We then minimize the following objective function given by the difference of dmt at xt minus yt whole square. This loss penalizes the differences between the predicted and actual noisy target image, ensuring that dmt learns to account for the domain shift. One key benefit of performing translation is in noisy space, the mapping becomes smoother and easier to learn. Clean image translation requires handling complex texture and detail, whereas the noisy representations filter out high frequency components, making the transformation more abstract and easier to model. After this translation, the denoising process takes over to reconstruct a high quality target domain image. Why not? Having described all three steps of the DMT pipeline, we now turn to a key limitation in this method, the challenge of choosing the optimal timestamp t at which domain translation should occur. Recall that during forward diffusion, we gradually add noise to a clean image x0, producing increasingly degraded representation xt as t increases. Similarly, in reverse diffusion, we start from a noisy version and gradually denoise to recover a clean image y0. Now consider this. If we apply a DMT too early in this diffusion phase, that is at a small t, the input xt is very close to x0, meaning that it retains much of the source image's content and low level structure. This may sound good, but it becomes increasingly problematic for domain translation. Because the image is not sufficiently abstracted, it still exhibits strong domain specific biases that make the source and the target domains significantly different. The model then struggles to learn a meaningful mapping from xi to yt. On the other hand, if we apply DMT too late, that is at a large time, the noise dominates. At this point, the image becomes close to pure Gaussian noise, and both XT and YT from their respective domains begin to resemble each other, regardless of the original semantics. The domain gap is minimized, but unfortunately, the content of the original source image is mostly lost. Translation under such heavy noise becomes semantically meaningless or unstable. This leads us to the central trade off of content preservation that requires a small t, keeping xt close to x0, and domain alignment that requires a larger t, pushing xt closer in distribution to yt. We want to balance these two factors. The insight here is that there is an ideal intermediate timestamp denoted by T star where these opposing forces are balanced. At this point, enough noise has been added to suppress low level style information and reducing domain specific differences, but not so much that we have lost semantic structure. We formalize this by seeking a timestamp where the distance between x0 and xt star is equivalent to the distance between xt star and yt star. In other words, the degree of corruption from x0 to xt star should be comparable to the domain translation distance from xt star to yt star. This equilibrium encourages the DMT to learn a stable, generalizable mapping across the domains. The main question that becomes, how do we find this optimal T star? And could we improve the results by either using multiple timestamps or assigning different timestamps to the source and the target images? These are precisely the direction we explore in the next section. To address the timestamp selection issue discussed earlier, we explore two alternative strategies designed to improve the translation quality and flexibility. The first strategy is multi-step DMT, that is also known as the fusion strategy, and the second strategy is asymmetric diffusion timestamps. Let's begin with the multi-step method. In the standard DMT framework, translation occurs once at a fixed timestamp t. The idea behind multi-step DMT is to perform translation at multiple time steps, for example, both T and T by 2, and then fuse the results to produce a more robust final image. In this variant, we obtain a translated image YT from XT. Separately, we obtain another intermediate image YT by 2 from XT by 2. Then, we take YT, partially denoise it down to time step T by 2 and produce YT2 dash. Finally, we fuse yt by 2 and yt by 2 dash using an auxiliary neural network, typically a unit. This fusion network combines two views of the image, one directly translated and one obtained via partial denoising, to enhance the quality. However, despite its potential, this strategy has drawbacks. Adding another model increases training time and computational costs. Moreover, experiments reveal that the fusion process can introduce inconsistency and noise, leading to lower performance in image quality matrices like FID. Thus, while multi-step DMT is theoretically valid, it may be practically inefficient. Okay, now let's examine the second approach, asymmetric diffusion timestamps. In this strategy, we remove the constraint that both the source and the target images must be diffused to the same time step. Instead, we allow them to be diffused to different time steps x naught to xs and y naught to yt, where s is not equal to t. This offers more flexibility. The forward diffusion process is written as q x from 1 to s, y from 1 to t, given x naught and y naught, and it is denoted by a joint probability distribution of y q xi given xi minus 1, q yj given yj minus 1, where I ranges from 1 to s and j ranges from 1 to t. We can observe here that t and s are both different, that is denoted by our method asymmetric, and the generative process becomes p of theta yt given xs into the multiplication from I is equal to 1 to I is equal to s of q xi given xi minus 1, and finally we multiply the result with q yj minus 1 given yj, here yj ranges from 1 to t. This formulation maintains the Markov structure of the diffusion process and remains probabilistically valid. By choosing S and T based on the task specific criteria, for example, how much noise a sketch or photo should retain, we can better control the trade off between content and style across domains. However, after thorough experimentation, we found that optimal performance still occurred when S equals T and both equals T star. This supports our original claim that performing domain translation at a carefully chosen single time step is not only efficient but also the most effective strategy in practice. To summarize, while both multi step and asymmetric time step strategies are valid and interesting, our original DMT method with a single shared optimal time step remains the best balance of simplicity, speed, and translation quality. Thank you.
Hello everyone, in this part of the talk, I will walk you through the experimental evaluation of our model, the Diffusion Model Translator or the DMT, focusing on how well it performs on several image-to-image translation tasks. We evaluated DMT on like four distinct eye-to-eye tasks. Image stylization, where we apply artistic style to a photo. image colorization, which actually involves coloring grayscale images and converting them to the RGB images. The segmentation to image, wherein we turn label mask into a realistic photos, and like sketch to sketch images, converting basic outlines into complete photo-like outputs. These tasks represent a wide variety of challenges, and testing across all four helps us to prove that DMT is not only versatile but also effective across domains. So for the to ensure fair and comprehensive testing, we have used like four data sets. First being a custom portrait data set. This is created using this Celeb AHQ dataset and the QMUPD model. Basically, the AFHQ dataset, which involves animals like cats, dogs, and wild species for for creating images related to them. Then there is like Celeb AHQ again, like for the segmentation based task, and then edges to handbags for the sketch to image generation. These we have used. For consistency, the all the images in every data set are been converted and reduced to 256 cross 256 so that a consistency has been maintained. Okay, we have actually compared DMT with five strong baseline methods. First being the PIX to PIX, a classic GAN-based model. Then the second being the TSIT, again a GAN-based model that uses cores to find features. Then we have used third place the SPADE, specialized for segmentation to image. Then the QMUPD, designed for like portrait stylization, and Palette, a DDPM-based model that injects input info at every step. These models represent both GAN-based and diffusion-based approaches, giving us the solid comparison between our model and all these baseline models. Now for evaluating our model, we have used various things like the FID. This basically measures how real the image generation looks, and the lower is the score, the better is the performance of the model. Then we have also used SSIM. SSIM basically evaluates the structure and layout of the image. The higher is the value, the better is the generation, and the better is the model performing. Then we have used LPIPS that actually checks how perceptually similar the image is to the ground truth. The lower the score of this is, the better the model is performing. We also have considered training and inference times and user scores to actually get a better inference of how well the images were created and how all things we got to evaluate easily. Let's have a look how we have actually implemented the DMT. This has been trained on PyTorch, like NVIDIA Tesla A100, as mentioned in the reference paper. Then the time steps are basically 1000 for all the tasks. DDPM uses are basically unit plus transformer sinusoidal embeddings to work. And the DDPM is frozen during DMT training. Using PIX to PIX and TSIT only generator block trading, then basically the DDPM is denoising is slow, replaced with DDIM basically, and F equals to 10 for like fasting sampling. Now in further slides, we will be actually comparing our DMT model with the classic image to image translation methods used in the industry and like proven from years. The methods basically include a SPADE, a segmentation image with classic mask, QMUPD, basically stylized with quality like guidance, palette, DDPM based condition generation, like peaks to peaks and TSIT as we talked earlier as well. Now SPADE. Let's begin with SPADE. It is like the design for segmentation to image translation, while SPADE uses category-wise segmentic mask and adaptive normalization. It struggles with like semantic information is corrupted or like incomplete. It does not produces well results. From the table 2, we can also infer like SPADE's FID is 66.55, while a model DMT brings it down to 36.78, nearly half. That's a massive improvement. And then SSIM increases from like 0.14 to 0.45. That's again like showing a model precise structure and much better than like the SPADE. The other basically the other scores as like LPIPS, L1 and L2 values are like very significantly low, measuring like fewer perceptual and pixel-wise errors, making it an overall better generation. If you look even the figure 5, the spades output often has like blurry faces and artifacts, especially around like hairlines and eyes. DMT, on the other hand, sharpens textures, add realistic lightnings, and maintain accurate face shapes. QMUPD basically used for stylization with quality guidance, built for even though it's designed specifically for a portrait stylization, TMT outperforms it. In table 3, QMUPD gets a FID of 12.81 while DMT scores 11.01. Okay, the lower is the better. The SSIM jumps from like 0.66 to 0.76, and the LPIDS also drops from like 0.2482 to 0.138, showing that the DMT captures stylistic features more precisely as compared to this QMUPD that has been even specifically trained for this portrait stylization task. In figure 6, we can say that QMUPD creates dull or inconsistent shading, while DMT produces more vivid colors, stronger brushstrokes, and even handles the fine details like eyes, hairs with precision. Now the palette task, it is a basically diffusion based model like ours, but a key difference is like palettes injects the source image at every single denoising step, making it very slow. Like even in the table 4, we will see that. Yeah, this is the table 4. Palette shows like good SSIM and stylization, but suffers in segmentation and sketch task. For example, FID in segmentation is like 40.7. Segmentation is like 40.77, while DMT goes down to 36.78, and it performs in scratch to image. FID, basically the matrix values have been compared. The bigger difference is its efficiency. Like palette needs 71 seconds to train 1000 images, whereas 21 seconds to generate just one image, like a huge difference. In contrast, DMT takes less than a second per image, and thanks to DMT and our mind setup sampling, visually in figure 8, as shown in this like slide, PMT results lacks texture and have flat colors or blurry edges, while the DMT keeps sharp lines, richer textures, and smoother transactions. And like on the similar basis, we have also evaluated the DMT versus pix to pix and like PSIT. The values are being referred as the table 4. These are all experimental values. And like in every task, the DMT is outperforming all of these baselines, proving it highly efficient and the performance is very good. Now, a critical part of DMT is choosing the right time step T at which we switch from like source to the target domain. There's a trade-off. If T is too small, the input is preserved better, but translation fails. Like we can see, uh, translation fail, image looks like incomplete. It is also too large, like if T is too large, domain shift is easier, but we lose content like faces change shape and poses drift and much more like inaccuracies in the images. From table from table 5 that we actually like see that our auto selected T gives nearly optimum results. For like segmentation, the T 200 will give the best FID and SSIM. For stylization, T50 balances all the things and gives the best results. Again, referring as to the like figure 7. Okay, figure 7 shows how image quality degraded at very low to very high timestamp. At t equals to 0, the hair textures like disappears. At t equals greater than 4000, the face rotates and loses identity. But at t equals to t star, that is the optimum value that we have choose, the results are both sharp and faithful to the input. And to this, the table 6 and table 7 also confirms robustness. Even t is slightly off, performance remains high, has been interpreted by the tables. Now, no model is actually perfect, and the same comes to our DMT aspect as well. Going towards the limitations of our model, limitations of DMT. So, like first limitation of DMT is the Markovian structure. Basically, it assumes that Markovian structure, so it's like applicable with DDPM or similar models. Like it believes the Markovian property like in both the forward and reverse diffusion processes. Like, and what is like actually the Markov assumption? Basically, it states the future state or the event in the sequence depends only on the current state of the event and not on the like past states of the events. Basically, what this tries to does is forming the image of like the next image just based on the like present image, not considering the past things and whatever happened out there. The other limitation is basically the requirement for the paired data. Like it requires paired data for training. This limit is used to like domains where unpaired samples are easier to obtain and it's like difficult to pair the samples and get the labels and all. The third limitation means like if the source and the target domain are too similar, like the DMT doesn't learn a meaningful transformation there and like it fails in that case. Matlab there and we might be aim to improve that in the future. Moving towards the final summary, or we can say conclusion. First is being like it beats both GANs and diffusion-based baselines on like 4 image-to-image translation tasks, as we have shown you statistically, as well as the photos and images. Second, it produces visually rich and semantic correct images, like performing outstandard. The trains and inferences are similarly, matlab, like significantly fast. It takes like much less time to get trained, and like, the values are produced in like no time as compared to other baseline models. Okay, it also adapts well across the tasks, such as a smart selection of translation time step, as we gone through the like selection process earlier. DMT sets are like new benchmark for practical high quality image to image translations. That actually comes to an end, and it concludes our diffusion model translator. And thank you all for your attention, and thanks for making it till the end.